All right, so welcome to our pre-recorded lecture for week 6. In this lecture, we're going to be discussing doubly linked lists, which is a different version of the linked list that we saw last week, which consisted of nodes that had a single link. And so to talk a little bit more about the differences between the two types of lists, I'm going to use a diagram here. So I'm going to switch over to my doc camp for a minute. And so last week what we saw is that in a singly linked list, each node had two attributes. One of the attributes was the element that it contained. So let's, for instance, some string element or some integer. And it also contained a reference to the next node. Okay, so in order to store the element, we have an attribute called self.x. Okay? And then in order to store the reference to the next node, we had an attribute called self.next. Well, with the doubly linked list that we're going to be taking a look at now, the node is still going to have those two attributes, self.x to store the element and self.next to store the reference to the next node. But now in addition to that, we're going to have a reference to the previous node as well. So we're going to illustrate that with an arrow pointing to the left. Okay, so in this case, self.x was the element string A. In this case, maybe we have something else. Let's just say B. And for this diagram in the singly linked list, there was no other node, so maybe our self.next is none. And in this case, let's just say that we actually do have another node. Well, in that case, these two would be holding the addresses to, well, in the case of self.next, it would be holding the address of this node, and self.previous would be holding the address of this node. So that's the main difference in terms of the attributes or the nodes in each type of list. Okay, so now coming back to the slides, we're going to take a look at what are the attributes of the list itself. Okay, so the list is going to consist of a dummy node that does not contain any data. Okay, the dummy node will still have the capacity to hold references to next and previous. And later on in the invariant, we're going to see what these are usually, how these are being initialized. But the other attribute that the doubly linked list has is the number of elements in the list, 10, which is something that we also had in singly linked list. And so the invariant, something that needs to be true at all times for the list, is that if the number of elements is 0, then this dummy node that we created, the references to next and previous actually point back to the same dummy node. And so we'll look at a diagram later on to get a better idea of what that looks like. But if there are more than, if there is at least one element, so if n is greater than 0, dummy.next is going to point towards the head, and dummy.previous is going to point towards the tail. Okay, so this dummy variable that we're creating, we're using it to help us keep track of where is the head and where is the tail of the doubly linked list. All right, so again, I'm going to switch back to my doc camp here. Even though we do have a diagram there from the textbook, but just so that we can do it by hand and get a better feel for works. This is the node called dummy that we're creating, and its next reference is going to be pointing towards the head of the linked list. Okay, so if this is our doubly linked list, it would be pointing towards the first node. Okay, so this is next. Now, its reference to previous is actually going to be pointing towards the tail. it's going to be pointing towards the tail of the doubly linked list. And so just to compare with how the textbook is illustrating this, we have this diagram in which the first node, which is this one here, the first node is the one that is called dummy. And as you can see, it has reference to next, and it's pointing towards the very first node in that list. Its reference to previous is pointing towards the very last node of that list. And because this is doubly linked, the first node, which is the head, also has a reference pointing back towards dummy. And so the head.previous would be pointing towards the dummy node. And similarly for the tail, the last element of our list, its next reference is pointing over to dummy. And so that's what this diagram is signifying. And as we see some more examples, we'll play around with the references. Now, one more diagram that I want to draw here is the case where we don't have any elements as part of the list. So basically, this case that's being described in the invariant. So what that'll look like would be the following. So this here is in the case where we have more than one element, and at least one element, I should say. If we have no elements, then we have this node dummy where its next reference is pointing to itself and its previous reference is pointing to it as well. All right, and that's just a convention that's being used. All textbooks implement the list in this manner. Not all textbooks use a dummy variable, a dummy node. And some that do use a dummy node will just have, if the list is empty, they'll have these references to the null. But just to stay consistent with the textbook, we're going to adopt that convention that if the list is empty, then the references for next point back towards the same node, and same thing for previous. Okay, I keep throwing this word around references. As a reminder, a reference simply means an address, okay, a memory address. So when we say dummy.next is a reference, we're just saying it's a way to keep track of where this other data point is at, where this other node is at. Okay, so we're keeping track of the reference or address of that node using the name dummy.next. But now let's go ahead and think about initialize. So initialize is referring to the constructor. And what we want to do is we want to create this dummy node and initialize it. Then we also want to initialize the number of elements to 0, right? Because in the constructor, we always want to first initialize the attributes of the data structure. And since our doubly linked list has 2 attributes, that dummy node and the number of elements, that's what we intend to initialize in this method. So the pseudocode would look something like this. And we would have n, which is keeping track of the number of elements. We would initialize it to 0. Then we would create a node called dummy. So here you see that we're assigning to it this new node constructor from the node class, but it's a very general way to write it. We're passing as a parameter the null element, because remember, dummy is not supposed to hold any elements at all. It's just a way for us to keep track of where is the head and where is the tail. Okay. All right, now when we first create a doubly linked list, we assume it's empty, so that means that dummy.previous, that reference to the previous element, is going to be pointing back towards itself, towards dummy. And the same thing for next. Dummy.next is going to point towards itself. All right, so we're now going to take a look at this get node I. So it's getting the ith node that is part of the list. And so one important thing to keep in mind here is that this is going to return the entire node object and not just the element that it is storing. Okay, so we'll see how we're going to actually be using this method to help in the context of other methods. So this is more of a helper method. This is going to help us retrieve elements and also insert new data into our doubly linked list. And so the general algorithm for getting the ith node is starting by checking the preconditions. So since we are specifying an index I, we want to make sure that that I is within the range 0 to n, including the 0 but excluding the n. If that's not the case, we might either want to raise an error or return nothing at all, in which this textbook we actually just returned the null element. Now, if I is less than n over 2, what that means is that the node that we're looking for is in the first half of the list. And so in that case, we're going to start at the head and work forward, meaning we're going to be following the links beginning at the head until we reach the index I that we're interested in. Now, if it's in the second half of the list, so if I is greater than or equal to n over 2, we're actually going to start at the tail and work backwards. That's because by doing this, we cut down the number of nodes that we have to visit in order to get to the node that we're interested in. And so let's take a look at a diagram to get a better idea of how that's working. So here I've gone ahead and drawn something with 7 elements. Notice that dummy, its next reference is pointing towards the very first element of the list, and previous is pointing towards the tail. I've kind of simplified this diagram a little bit in that technically the reference for the head's previous should be pointing back to dummy, and the reference for the tail's next should be pointing also to dummy. But just to minimize the number of arrows that we're looking at, since we're not really interested in those at the moment, I've just omitted them. Okay, but typically we do also have those links going back to dummy. But for now, let's say that we call get node at 2, right? So that means we're interested in this node. And I keep saying the word index, but we want to keep in mind that because this is not an array, in memory, this is not indexed, right? There's no nothing behind the scenes that associates A with being at position at 0. This is just an indexing that we're doing, or that the user is also thinking about storing the elements in a linked list. Okay, but these do not exist behind the scenes like they do with arrays. Okay, so when we are trying to get node at 2, we said the number of elements here is 7. So when we compute n over 2, we're going to get a 3.5. And that means that 2 is less than 3.5. So we're in the first half of linked list, which of course we can also see just from the drawing. That means that we're going to start at the head. And we're going to start by maybe naming the node P to be dummy.next, or in other words, we start at the head. Okay, from there, what are we going to do? So P is currently pointing towards this node. It's not the one that we're interested in, so we're going to follow its reference to the next node. And so we're going to call P.next. Okay. So this is .next at the moment. Now that we've made it here, I'm going to reassign this to the name P. Okay, so that P no longer is pointing towards its head. Now this is P. All right. And again, and now this is P again, because this node is not the one that we're looking at. It's not the one that we're after. This is the one at what we're considering, quote unquote, index 1. we want to move on to the next one. So we're going to say if this is P, this is P dot next, right? We're following this reference P dot next, and then we are going to reassign that to be P. So we're going to say P dot next here. So we started with the head, and then by calling dot next on the head, we made it to the node that is containing the element B. And then by calling next on that node, we made it to the element C. In terms of the indices, originally the P was the element corresponding to our made up index 0, and then P dot next was our made up index 1, and finally we made it to 2. So at that point we would stop, right, and then we would return this node P, which is no longer this, but just this. Let's say on the other hand that we're trying to get a node at our made up index. Now we want this one. If we start at the head, in order to make it to that index 4, we're going to have to visit 4 nodes that are not the one that we are looking for. If we start at the tail, however, we would only have to visit 2 nodes that are not the ones that we're interested in, and then we would have access to this node containing E. And so let's take a look at what that process would look like. We would start with P being dummy. Okay, so this is where we have a little bit of flexibility as to how we can go about it. We can start with dummy.previous, right? That would start us at the tail. And then from the tail, we would follow previous, so P.previous. And then we assign that to be P. Okay, so now P is pointing here. And then do it one more time. We want the previous node to it, so we would follow this link, which is P.previous. It would give us this node. And so now this is the one containing E. This one was F. This one was the one containing G. Well, we assign that to be P. So then P is going to be pointing towards the node of index, the one at index 4. So that's one way that we can go about it. The textbook, though, just stay consistent with the textbook. The textbook actually begins with P being just dummy. Okay, so just this node, this dummy node up here that doesn't have any elements. And so from there, we would call P.previous, which takes us to the tail. Okay, so then we reassign P to be P.previous. And now this is the tail. We would need to perform 2 more P.previous calls, right? Because we need to go from the tail to F, so that's one call, and then from F to E, that's another call. Okay, so then now this would be like index 6, this would be index 5, and finally this would be the index 4 that we're looking at, after. So the main reason why the textbook decides to go down this route is because then the number of iterations becomes n minus I as opposed to n minus I minus 1, which would, I guess, be a little bit more difficult to remember. Okay, but this is n minus I number of repetitions where we assign P to be P.previous. Okay, these would be n minus I minus 1. Okay, so like in our case, the n was 7. The I that we're interested was that's already 3, and then minus 1, that's 2. 2 of these p dot previous is p. Whereas for here, we just have the number of elements, which is 7, minus I, that's a 4, so we get 3. So either one of these implementations, though, would work. But if you're taking a look at the textbook and you're seeing your minus I, that's because they start with p being dummy, as opposed to dummy dot previous. Okay, so let's take a look at that pseudocode now and come back to the slides. And the pseudocode looks something like this. We check the precondition. So if I is less than 0, or if it's greater than n, then we're going to return null. If I is less than n over 2, that means we're trying to obtain a node that's in the first half of the list. We assign p to be dummy.next, and then repeat I times the overwriting of p with p.next. Okay, so we follow those links. Otherwise, if the node is in the second half, we assign p to be dummy, and then we repeat n minus I times the operation of assigning p dot previous. And then that would place us at the correct node, which is being stored in p, and we would just return that node. We would just return p. Okay. So that actually facilitates quite a bit the get and set methods for the doubly linked list. So get I is supposed to return the value of the ith node, and with the method that we just implemented, all we would have to do in get I is check the precondition, and then find the ith node by means of get node I, and then return its value. So return the value x that it's storing. For set ix, we're trying to set the value of the ith node to this new value x. So what we would do is, again, check the precondition. Then we would find the ith node. We are going to create a temporary variable to store what is going to be overwritten. So in this case, we're calling that temporary variable y. And then we would just set the new value and return y. Okay, so the pseudocode is going to look like this. If I is less than 0 or I is greater than or equal to n, we're going to raise an exception. And then otherwise, we're going to return get noded I, so we're going to get the ith node, and then dot x. This is accessing the value, the element that's being stored in the node. Okay, so this is just going to return the element rather than the entire node. For set ix, if I is less than 0 or greater than or equal to 10, again, we're going to raise an exception. Otherwise, we're going to get the ith node. In this case, we're calling it u. The ith node we're going to call u. We're going to store the current value, which is u.x, into this temporary variable called y. And then we're going to reassign the value of u.x to be this new value given by the parameter x. And then finally, we return the contents of the temporary variable y. So if we think about what is the running time for these operations, this is going to be determined by whether we're looking in the first half or the second half of the list, right? It's always going to be the minimum of looking in the first half or looking in the second half. So that would be the minimum of I and n minus I. You see that we also have this +1. +1 is because we have an initial setting for p. So like if it's in the first half, we had p is dummy.next, and that counts as 1 visit, and then plus whatever number of repetitions we had to the visits to next. Okay, so let me backtrack to this slide here. And so, for example, we're in the first half. This counts as 1 visit. So that's one. And then we repeat I times visiting the next node. All right, so that's in the case of the first half. In the case of the second half, we assigned to P dummy n minus I times, where we visit the previous node and assign it to BP. So if we think about then what is the runtime? It's going to be 1 plus the minimum of these two, repetitions. We're now going to take a look at this method called add before. This is meant to be used as a helper function. So it's actually going to facilitate the implementation of other methods in the doubly linked list class. So it takes two parameters. It takes a node W and an element X, and its purpose is to insert a new node before the node that we are labeling W. Okay. So here is, let's go ahead and draw a diagram to get a better feel for what's supposed to be happening during this operation. So I'll switch over to my DocCam. Let's say that we have an initial list. I'll draw one more node that looks like this. And just to facilitate the discussion, I won't be incorporating dummy quite yet. Okay, let's just for now that we have this doubly linked list, and this node that contains the element D is called W. Then our goal is to insert a new node right in between these two nodes, right before this node that we're calling W. And so the very first thing that needs to happen, of course, is we need to create the node to contain the new element. Okay, so we would create the node, insert the new element, we're given X. And then we have to create the links between this new node and the position where we want to place it. Okay. So we could start with, and then this is actually referenced as U. Okay, so the name of this node is U. So we can start by taking its reference to previous and pointing it towards this node that contains C. So what would the name or what would be the label of this node? How are we able to access it? Well, we have access to this one, right? We have access to one containing D, it's called W. We could follow its reference to previous and get access to this node. So the way we're going to gain access is through w.previous. Okay. So for this very first operation that we're doing is we're taking the new node and setting its reference to previous to be w.previous. Then we need a reference next, right? We need to link its next to point towards this node called W. We're going to do this. And what that's going to look like is u.next is this node called W. Okay. So there's a couple more things that need to happen. And that is I need to change these links, right? I need to change so that this points back towards the new element. So the w.previous has to go to the new element. And then we also need to change the reference next in w.previous to point towards the new node. So there's a couple ways that we can go about to avoid having mistakes from overwriting the W. What we're going to do is or the references to like w.previous or w.next. What we're going to do is we're going to just write it in terms of this new node U. And what I mean by that is this. This node containing C has now two references pointing towards it. It has the w.previous, right? It's this one. It also has this u.previous. So what I can do is, this is also known as u.previous, is set the reference for next, which is now this one here, to point towards the new node. So this now gets reassigned. And it's going to point back to this new node. All right, we have one more link that we need to change. And that is the one here. The previous has to go back to U. So again, there are two references to the node containing D. One of them is from W, the other one is from this new node U. Okay, we're gonna use the one from the new node U. We're gonna say U.next, which is this one. Previous, which is this link, has to point back to the new node. Okay, so U.next places us at this node, and we want previous, meaning this link, to be reassigned to the new node. Now we do this. So the end result of this is now a list that contains the original elements, but this new node U containing X has been inserted right in between C and D, right before the node known as W. So the pseudocode is going to look something like this. Well, I guess we can go first through the English algorithm. So we check any preconditions. Then we're going to create a new node U. We're going to update the references to next and previous for both U and W. And then we're going to increment the number of elements by 1. So this is what it would look like. The precondition that we have to check for is if W is null. In that case, we don't have references to previous or W, so we would have to throw an exception. Otherwise, we're going to create the new node with the element X that was given to us. We're calling it U. Then we set U.previous to be W.previous. We set U.next to be W. Okay, so here we're setting the links for previous and next of the new node. Then we do U.next.previous is U. Okay, so U.next is the same as node W. So this is just W. We're setting the reference to previous in W to be the new node. Okay, then we take U.previous. Remember, U.previous was pointing towards W.previous. So the node that comes originally before W. And we're setting its reference to next to be the new node U. Then we increment n by 1. And in this case, we return U, which is the new node that was created. We return a reference to that new node in case we want to do any additional computations with it. All right, so now that we know, now that we've implemented this add before node W, it's a lot easier to implement the method add at position I the element X. So what we do is we check for preconditions, where again, if I is involved, we want to make sure that we have I between 0 and n, exclusive of the n. And what we do is we find the ith node with the method that we just implemented. We insert a new node u that contains x just before it, and then we return u. And so thanks to the method we just wrote, the pseudocode would look like the following. If I is less than 0 or greater than or equal to n, raise an exception. Otherwise, we're just going to return add before get node I, comma x. Okay, so we implemented both of these get node I and add before in the previous slides, and here we just get to call it as part of the implementation for added ix. And since the get node method runs in big O of 1 plus the minimum of I and n minus I, then automatically this add I and x is going to have the same runtime. Now we're going to take a look at this last method, which is remove I. Remove I removes the ith node. And to get a better idea of what's supposed to happen, again, we're going to take a look at a diagram. Okay, so let's say that we have this linked list, and we were trying to remove the ith element. Let's just say it's this one here. We're going to call that ith element the node w. And so we've already written a method that can allow us to obtain the ith element. Okay, so let's just say we call remove I. The very first thing that we would want to do is get the ith node by means of get node I. We're going to call that w. Okay. And so what would need to happen next? Well, we would need to put all references to this node. And besides this external reference that we have right now of w, there are two other ones that are pointing towards this node. There is the one coming from the node containing b and the one from the node containing d. So our goal is to reroute those links so they skip over this node called w. So how can we do that? We could first take the link and reroute it to just D. Let's think about how we would do that. In order to gain access to this node, we would go through W and then look at the previous, at its link to previous, right? That's how we obtain access to this node. So we would want W previous dot next, right? Because that previous brings us to the node, and now we want its reference to next. So dot next to be this node here. So if this is W, we can go to this node by means of the next reference. So this one is called w.next right now. And just like this one is called w.previous. Or we can reference it, but we can access it through those references. So we're going to have that w.previous next should be this called w.next. Now we no longer have this link to the middle node, or to the ith node. Now we want to reroute the reference, okay, so that it no longer points to W, now it points to w.previous. So how can we do that? Well, again, the name of this node, it's being referenced as w.next. And then we would want its reference to previous to be w.previous. So this is w.next. Its reference to previous has to be this node, which is called w.previous. And then from that, we would just reduce the number of elements by 1. So we'll do n is equal to n minus 1. And since we want to be able to return the node, we would eventually just return the contents of that node. So w.x, w depending on the implementation that the textbook is adopting. So let's see what the pseudocode would look like. We would have, again, get node gets assigned to w. w.previous.next is w.next. w.next.previous is w.previous. And then n gets decremented by 1. Okay. In this case, they're not really returning the value of the ith node, but if we wanted to, we could just write return w.x. All right. So how many operations are happening here? Just in remove, we're not thinking about what's happening within get node. Just within remove, it's a constant number of operations that involve 3 nodes, right? It involves the node w, w.next, and w.previous. So that's considered to be constant time, since we don't really have to travel through any additional nodes. All right, so to finalize this discussion, we're just going to go over some runtimes. The DLList list is going to implement the list interface, and this has methods get I, set ix, add ix, remove I, which run in big O of 1 plus min of I versus n minus I time. For the queue operations, if we wanted to implement the queue, we would implement the add x, which will be the same as add at position 0 the element x. And that takes a constant number of operations because we're just dealing with the first element. For remove, we would call remove at n minus 1 because we would just want to remove the tail. And then for stack, push would be add 0 at x, which also runs in constant time. Pop would just be remove 0. I think this here is a typo, should say remove. And then the deck operations, which are add first, add last, remove first, and remove last, those are now also going to run in constant time. So add first would just be add at 0x, add last would be add at nx, remove first would be remove 0, and then remove last would be remove n minus 1. So what's costly in a DLList list is finding the relevant node, because as we saw, we have to travel through at least half, at most half of the list, right? But it's still more than one node that we have to visit in order to make it to the node that we're interested in. In an array-based list implementation, which was the last module, the relevant array item would be found in constant time because we had the memory addresses of the specific locations. However, for removal, it required shifting of the elements in the array, and that wasn't constant time. Okay, so for this reason, in a linked list, these are well suited for applications where the references to list nodes can be obtained through external means. So just like in the case where we artificially had a reference W to a node of interest. In general, if you want to be able to implement a queue or a stack efficiently, then linked list would be the best data structure versus an array-based list, because an array-based list contains the shifting. So that is all for the linked list discussion. At this point, you are now ready to experiment with this data structure by means of your lab number 2. So I highly encourage you to get started on that. And if you have any questions, I will be holding my office hours throughout the week at the usual time. Thanks so much for tuning in.